So now, without further ado, I'd like to welcome Martin Kleppmann to talk to us about conflict resolution for eventual consistency.
Thank you very much. Hello, everyone. I did think it was pretty nice that the sum total of my organizational effort with this was writing one tweet. And then I get to meet all of you wonderful people. So thank you for coming. The stuff I'd like to talk about is kind of the research that I'm working on. But firstly, briefly, you might have seen... Sorry, I need to actually plug this in. This book I wrote recently, you might have seen, which is on data systems architecture, on like choosing what database to use for what purposes, for example. That's been keeping me busy lately. But now I'm at a university in a research job, and I'm working on this project we're calling True Data. The high-level idea with this is we're trying to help build the applications in the way that we have at the moment for building collaborative applications, but without having to trust servers so much. So trying to put end-to-end encryption into just the base layer of how systems work. And so as part of that, what we've been working on are the kind of algorithms that make collaborative applications work and see how we can adapt those in a way that has better security features. So the context of the systems I'm talking about here, you can imagine a bit like this. So scenario is this. There is you, a little blue stick figure, and you are hacking on some code. And this is a timeline, time going from left to right. And at some point, you decide to commit that code to your favorite version control system, let's say Git, for example, here. And then you want to share that with your colleagues. So you push that code to some place where others can get it, say GitHub, for example. Now, while this is happening, concurrently, one of your coworkers in red here is also hacking on some code and also decides to commit some code. And as you probably know from these kind of workflows, then a merge has to happen. And now if you've been working on two different files, then Git will just do the merge for you. If one of you has touched the beginning of the file and the other has touched the end of the file, then probably the Git merge will still be automatic. If your changes got too close to each other, then Git will tell you to resolve the merge conflict by hand. And then things start getting a bit annoying. But it's not just code that behaves like this. So we could instead talk about Word documents. Say this is the way how lawyers work, for example. If they're some teams of lawyers negotiating a contract or something like that, they will actually email Word documents back and forth. That is the way the collaboration works there. And so you can have exactly the same kind of process, potentially, that two different parties are editing the same document at the same time. They save it, and then they send it by email from one to the other, and then somebody has the job of merging these things. This is even harder with Word documents sent by email because, as far as I know, Microsoft Word doesn't have a built-in three-way merge tool that would make this kind of thing easy. So it actually becomes a whole lot of manual copying and pasting and such irritation. But the point I'm trying to make here is that the data flow, the general pattern, is exactly the same. In fact, it's the same picture. I just changed the labels on it. So what we have here is the state of some shared data structure, in that case the document, is being edited concurrently by two different peoples, which mean that those different states diverge, and then those divergent states need to be merged together again. So you might think, oh, we have Google Docs, and that lets several people edit a document at the same time, and you would be right. And so what it looks like in that sort of setting is, again, let's say you have a document containing the text hello, and now one user edits it and inserts the word world to make it hello world ! And the other user concurrently adds a smiley after the exclamation mark. And so you can say, well, these are two different edits. They're quite close together, but we can quite reasonably merge them together. And so as the blue user tells the red user about the smiley, and the red user tells the blue user about the word world, they get merged together to say hello world ! Smiley. And this seems like a reasonable automatic merge. And this is, in fact, what happens in things like Google Docs or Microsoft Word Online, which let you edit collaboratively some document together with other people. So what happens actually in those kind of documents is you still have a copy of the document locally on your own machine, running inside your web browser typically. But and whenever you want to make some change to that document, that is, you press a key locally, that change gets immediately reflected on your own local copy. You don't wait for a network round trip to some server before applying that change to your local copy, because that would be too slow and it would be a pain in the neck to type so slowly. So instead, that change gets applied locally immediately, and then asynchronously gets sent over the network to anyone else who's collaborating on this thing, which means that you do get this temporary divergence, the different versions going on in parallel. It's not as coarse-grained as with the git commit example, where like somebody might work for days on some commit and then has diverged quite significantly. With something like Google Docs, you'll probably just be diverged by a second or two unless you're working offline. So more abstractly, the kind of systems we are talking about here, you can think of as you've got a couple of nodes. A node is just a computer or a mobile phone or laptop or whatever. It could also be a server in a data center. I don't really care too much. Each node has some data locally stored on it, and that data can be changed by users. And so here, a red user can come and change the data on node I, and then that change needs to be propagated to the other nodes that also have a copy of this data. And in this example with the collaborative editing, as I said, you can also have another user who concurrently comes and changes the data on node J, and that change then also needs to be propagated back to the others. So this very similar pattern, actually, I explained with Google Docs because that's kind of a familiar environment. Actually, with some distributed databases that you get in very large-scale deployments, actually very similar patterns happen there. In that case, these nodes would be servers in different data centers spread potentially geographically across the globe. But actually, the general pattern is very, very similar here. And in particular, one of the things that we want with these types of systems is that different copies can work independently from each other, even if the network is a bit messed up. So say temporarily one of the nodes is partitioned from the others. That might mean that it's offline, maybe just because it's a mobile device and it doesn't have an internet connection right now, or maybe because there's some disruption in the network infrastructure. For whatever reason, the messages don't get through right now. But we still want the red user to be able to make changes to the data on node I, and for the purple user to be able to make changes on J. So the fact that they can't talk to each other right now shouldn't stop them from making edits. So how do we make this kind of merging work? So there are two families of algorithms that I'd like to talk about a little bit. And these are the types of algorithms that will allow these kind of merges of divergent data to happen automatically. So you don't have the manual merge conflict resolution that you do with Git, but more like the automatic merging that you do with Google Docs. So on the left-hand side, operational transformation. Has anyone heard of this term before? Cool, a few. So this is what's used in, for example, Google Docs, and I'll give an example later to just demonstrate how it works. One of the key issues with it is that it requires all of the changes to go via a central server. There's an alternative family of data structures called CRDTs, which stands for Conflict-Free Replicated Datatypes, which still trips me up every time I try to say it, which is the area that I've been actually working on in my research. The biggest difference to OT is that it doesn't require a central server, so it can work with any kind of network topology. So what I mean here with central server is with Google Docs, say, with Google Docs, if one user wants to make a change and propagate that to another user, that change has to go through a central server, and that server sequences all of the changes. So it applies a total order to the changes. And that is kind of okay if you're collaborating with someone on the other side of the world, but I find it a bit ridiculous if you're trying to exchange data between, say, your phone and your laptop, and the distance between those two devices is about 30 centimeters, and they have probably a local Bluetooth connection between the two of them, and still the algorithm that Google uses for Google Docs will not allow it to use that local network connection because the algorithm requires that all of this sequencing goes through the central server. So you end up having to send everything to some data center somewhere on the other side of the world, and that's kind of annoying. So what I'd quite like to do is to be able to support more flexible kinds of network topologies, where you can say, for example, the blue user has 2 devices, the red user has 2 devices. Those pairs of devices can talk locally over whatever network they happen to have available, might be like a local Wi-Fi or Bluetooth or something. And they should just be able to synchronize between the 2 devices, even if they can't reach the internet right now. And even if they can't reach the red user's device. So you can have these 2 actually partitioned from each other, unable to talk to each other for some amount of time. And that should be okay. And then at some point later, when they reestablish internet connection, then they should be able to merge together their changes and progress. So these are the kinds of communication patterns that CRDTs will support. And this is the point where I'd like to introduce you to a bit of code that I've been writing. So this is open source on GitHub. It's called Automerge. It is research code, which means do not use it in production, please, because it's going to break and it's not very efficient yet, and so on. But it's quite an interesting exploration of this topic, and I am hoping that over the years as we work on it, it will actually turn into something robust enough that people might use to build real applications. So Automerge you can think of as a kind of data model layer on top of which you can build applications. So it provides a kind of storage abstraction, very much like JSON, and you can use that to express some data structures that your app cares about. So like if it's a to-do list, for example, then it would be a sequence of to-do items. If it's a shared text document, then that would be a text, a long string with maybe some formatting metadata. The idea is that many different kinds of applications can be built on top of it. It's implemented as a JavaScript library at the moment, so it works in browsers and in Electron. We've been mostly prototyping it with Electron, actually. We built like a sample Trello clone as an example of what you can do with this sort of thing. And another interesting part of this library is that it's agnostic of the actual network technology used. So as one example of how you can, like, somehow you have copies of this thing on several devices and you need to get the data from one to another. And Automerge doesn't care how that network transmission happens. One way of doing it is in a peer-to-peer fashion. So this is kind of interesting and exciting technology-wise. Has anyone played with WebRTC before? No? Okay, so WebRTC is a technology that's built into most modern web browsers. It's actually intended for things like making video calls or audio calls over the internet, and it deals with all of the really annoying network gubbins to actually make peer-to-peer networking work. So like UDP hole punching to get through firewalls and get through NAT, and it's all the really ugly, nasty networking stuff they've kind of packaged up there. You can use it for audio and video, but you can also use it for data. And so that's what we've done, is just sending small JSON messages over the network. And so provided you have some way of establishing this kind of connection with the other person, you can actually send messages to them without those messages going via any server, which I find kind of cool because, like, often when we're building stuff on the web, everything goes via servers. And so it's nice to just play with that assumption and see how far we can get without servers. But you could make this work with servers, of course. So like another perfectly reasonable implementation would be to have, say, a WebSocket server, where one client sends their changes and the server then just echoes them back at everyone else who's connected to that document. Or you could imagine sending it via Tor, which is an anonymity network. If it's like really sensitive data, if you want to protect the communications of, say, dissidents under a repressive regime or something like that, then you might actually care about this sort of thing. So idea being that the network layer is very flexible. Automerge itself doesn't really assume anything about what it looks like. Our goal, as I said at the beginning, is actually then to slot an end-to-end encryption security layer in between here as well. That is actually a to-do item at the moment, so at the moment it's all completely unsecured. I think I might talk a bit about the algorithms that make Automerge work, because they're quite interesting and just like intellectually interesting. But before I get into that, I should talk a bit about like what it actually achieves. So I mentioned earlier informally this idea that, okay, someone makes some change, someone else makes another change. We want those to be able to merge together. So what we require is some kind of consistency model to talk about, like, what is it actually that this algorithm achieves. At the end, we want something that people often call eventual consistency. That is, it's not the same as like a database where you have serializable transactions or so. It's more something where we're a bit vague about allowing people's different views of the data to drift apart and then merge back together again. Now, I have a bit of a problem with the term eventual consistency, which is why I want to unpack it a bit. Because it's actually a very vague thing. Instead, I want to break it down into 3 criteria. And one is that really what we want is we've got some kind of messaging system going on here. That is, whenever I make a change to the document, I send a message to everyone else describing what that change looks like. And we want eventual delivery of those messages. So this is really just saying that, assuming that devices are not offline forever, that eventually a device will come back online, then at some point, if I make a change, then it will be delivered to that device. But I'm not making any timing guarantees. So if someone goes hiking in Iceland, where they have no cellular data reception, they come back 2 weeks later, then you have essentially like a packet delay of 2 weeks in your network. That's okay. So making no timing assumptions here whatsoever. But what we do want, this is really important, is convergence. And that is, if 2 nodes in the system have seen the same set of operations, but maybe in a different order, then we want them to end up in the same state. So if you have the combination of these 2, that is, messages eventually get through, even if you have to retry, keep retrying, but eventually messages get through. And if you've got the whole set of messages, then you're in the same state as everyone else. That's a nice property. That means you're going to eventually end up in the same state as everyone else. One more criterion I like to add on here is we like to try to not lose any data in the process, because like one way of achieving convergence is we're going to say we're going to always throw away all changes made by Bob. And that is a perfectly valid way of achieving convergence. Like only Alice's changes are accepted, Bob's changes are always rejected. Sorry, Bob. It kind of meets the formal criteria, but it's not very useful. And in fact, people would probably be a bit annoyed if we do that. And so this is kind of like the non-trivial condition that we add to it just to rule out that case. Okay, so we can structure data as JSON. This is a to-do list, for example. And if we want to represent this kind of structure in something like Automerge, we have to break it down into its main constituent data structures. The first of which is there's some kind of ordered list going on there. So the square brackets represent some sequence of things that have an order. And then there's some kind of maps that can be nested inside each other, or JavaScript objects. So some kind of key to value mapping. And once we have a structure like that, we can change it in various ways. So one way we can change it is, for example, to assign a new value to a key in a map, overwriting, for example, false with true. That would be like what happens if somebody clicks the checkbox saying that they've done this item on the to-do list. Another type of edit that you might do is editing a string, so changing buy milk to buy soy milk, for example. Another thing you could do is insert a new item into a list at any position in the list. Or you might add a new key into one of those key value mappings. And we support all of these different kinds of changes. And the code for it looks something like this. So if you focus on the middle bit first, you have some doc, which is a JSON document. And in it, there's something .todos, which appears to have been initialized to be a list or an array. And push is just a regular JavaScript method for appending a new element at the end of an array. And so this API supports just the regular JavaScript API for making changes. But actually, the state object that you pass in here, that represents the entire state of your data at the beginning of the time, that is actually immutable. So we never actually make any changes directly to that, but instead you pass in the old state, you do this block that describes how you want to change the state, and you get back a new state object in which that change has been applied. And while you're applying the change, you get the chance to apply to add something like a commit message to it. So in the version control system, you would call this a commit message, or here you could call it some kind of annotation. This is just like a human readable thing that describes the change. It's optional, but it's kind of neat for being able to visualize the history of what happened. And then here, there's this callback, and it provides this doc object, and only within here you can use these mutable methods like push. So since I said the state itself is immutable, but within this, this is implemented in JavaScript as a proxy object which intercepts all of the calls that you make. So you can just assign things here, overwrite stuff, whatever, and all of those get captured by Automerge. And Automerge then essentially makes a log of the changes that have happened here. So within this here, you can just use plain JavaScript objects and the typical methods. But what this translates into internally is this operation log. And this is kind of the fine-grained stuff that you wouldn't want to have to write by hand because it would get extremely tedious. So I'll just go through it line by line briefly so that you get the flavor of what's going on here. So you can create a new map object, an empty map object, and it's given some ID, ID1. And then within that map object, we assign the key title to the value buy milk. We assign the key done to the value false. Both of those are attached to this ID1 object. Then we have some to-dos object, and we insert a new list element into that and give it some identifier. And then we link that new map object that we created into that list. So this is all the very tedious work, but this is actually what has to go on in order to make the CRDT work. So as I described earlier, what we want to support is that you can actually have several users making changes, arbitrary changes, on different nodes, and we want to be able to send those changes packaged up in some way to everyone else who also has a copy of that data on their device. And this kind of log is the form in which those changes are sent. And then there is a bunch of logic internally in these data types which ensures that even if different people see the changes in a different order, they will actually end up in the same final state. We have a convergence guarantee. This is what I mentioned earlier. So the idea that having received the same set of operations, our data type can promise that you will then be in the same state. If you've not seen all of the operations, then we can't promise that you're in the same state because you're missing some information. But under the assumption that you've seen the same set of operations, then we can promise that you will be in the same state. Okay, so I think I should show how these algorithms work, because this is kind of where it gets interesting. So I'll first show how Google Docs does it, and then which, as I said, requires the central server. And then second, I'll show how the CRDT that we're using in Automerge does it. And so I'm taking here as example a text document containing the characters HELO. So we can treat a text document as a list of characters and just give them indexes like here. And now we can have two different users concurrently making changes. And so let's say the user on the left inserts a letter L to read hello properly, and the user on the right inserts an exclamation mark at the end. And so we now want to propagate those changes to each other and end up in a sensible state, which is probably hello exclamation mark. And so the way the operational transformation algorithm of Google Docs does it is as follows. So each change is captured as an operation, and the operation looks something like insert exclamation mark at position 4. So you can see here in the numbering, starting with 0 for H, the exclamation mark appears in position 4 here. Whereas on the left-hand side, we insert L at position 3. So this second L is the new one that was inserted. And now those get propagated. So the insert L at position 3 gets forwarded to the user on the right-hand side. And this user now applies that operation to their own local copy. And so the insert L at position 3 does the right thing. So we get hello exclamation mark. But if we go in the other direction, you see here, if we want to end up in the same state at the end, we can't just take the message insert exclamation mark at position 4 and send it to the left-hand side. Because if we insert exclamation mark at position 4 here, we would actually end up with hell exclamation mark O, not hello exclamation mark. So what the server here has to do is to transform the message. The server has to notice that actually there was an insertion before this position 4, and therefore the position 4 has to move along by 1. It has to change into position 5, and this insertion of the exclamation mark on the left-hand side now has to happen at position 5. And this is fundamentally the reason why Google Docs requires that server, because it has to keep track of, like, well, did this insertion at 3 happen first, or the position insertion at 4 happen first? And it decides on this order, and depending on what has happened concurrently, it then has to transform the coordinates or these indexes of the changes in such a way that when they get applied out of order on a different copy, then you still end up in the same state. These algorithms get pretty mind-bending pretty quickly, and operational transformation does have a reputation of being an absolute nightmare to implement correctly. So instead, CRDTs approach the problem in a different way. And rather than talking about the indexes of each letter in the text document, we're just going to give each letter a unique identifier. And I'm going to use a simple scheme for making those identifiers. I'm just going to take a number, which is just like a counter that keeps increasing, and attach to it a letter, which is a node identifier. So we have on the left-hand side node A, on the right-hand side node B. And we're just going to say that all of the letters that are created by node A get a letter A, and all of those that are created by B get a letter B. And now we can have the same change happening on both sides. And we're going to create a new identifier for the newly inserted character. And so the rule I'm going to use is, for the number, pick a number that's 1 greater than any of the numbers you've seen before. So the greatest there was 3, so we'll pick 4, and A, because this is generated by node A. And on the right-hand side, again, the same rule. We pick the same number, 1 greater than the greatest you've seen before, so makes 4. But this is generated by node B, so it gets 4B. So this simple rule already ensures that these identifiers are unique, because each node will generate a particular number only once. It'll keep incrementing after that. You can end up with the same number 4 on both sides. That's fine, because A and B are distinct. Okay, so now we've given 4A and 4B as identifiers to these, and now the messages that we use to describe these changes, the operations, they look like this. So on the left-hand side, we have insert L, and we say the L is given a new ID of 4A, and we're going to say insert after 2A. because so 2a is the letter that appears immediately before it, or rather the ID of the letter that appears immediately before it. On the left-hand side, I'll say, on the right-hand side, I'll say insert the exclamation mark. 4b is the new identifier. 3a, which is the letter O, that is the ID of the character that comes immediately before it. And now the nice thing with these messages is that we can simply forward them. The server doesn't need to do any transformation here. In fact, the messages can be encrypted and the server doesn't even know what messages it's forwarding, and it still works. So here, this insert L with ID 4a after 2a. Well, we find the letter with ID 2a, that's this L, we stick the 4a after that. And then on the left-hand side, similar, we take the exclamation mark with ID 4b, we look for the position 3a. 3a is the O, we put the 4b after 3a, and so it puts the exclamation mark in the right place. Okay, so far? Can anyone see a problem with this? If you delete 3a, yes, that could happen. The solution to that is simple. We cheat with deletions, and we don't actually delete, but we just mark the characters as deleted, but actually secretly keep them in there. And so that way they can still be used to identify a position. Any more problems people can spot with it? Yeah, if they're both inserting after 2a or both inserting in the same position. If they're both inserting in the same place, let's look at an example of that. It still works, but it's a bit more subtle. So, hello. Sorry, my PowerPoint has just frozen up. Right, so inserting in the same place. So let's say we want to insert between A and B. So directly after A. And on the left-hand side, I'm going to insert XY. And on the right-hand side, I am going to insert PQ. And so what I expect now as a final merged outcome is that XY and PQ, they must both appear somewhere in the space between A and B. So they certainly shouldn't go wandering off somewhere else into the document. We know that they should stay between A and B. Those are like the right and left bounds. And I want X still to come before Y, and I want P to still come before Q. So I'm just going to say that reasonable merged outcomes of this are either A, PQ, XY, BC, or A, XY, PQ, BC. So both of those are reasonable. We don't really care which, because it's arbitrary. They're happening concurrently. So let's apply the same rules for generating IDs to these. So like before, the rule is for the number, pick one greater than what you've seen before. So here 3, then the next one we pick is 4a, the next one we pick is 5a. On the right-hand side, we have the same. We pick 4b and then 5b. So that's as it was before. Now we're going to send this operation for the p from the right-hand side to the left-hand side. So here we're going to say insert this p with ID 4b, the new ID that we generated, after 1a, because 1a is the one that comes immediately before. And so we're going to stick it here. We're going to find 1a and put the p after the a. And then similarly with the q, we come along. The q has ID 5b inserted after 4b, right? So inserted after this p here. And that works because we've already applied the p on the left-hand side. 4b, that position already exists. So we can use that as our reference point, insert 5b directly afterwards. Okay, so in one direction, this has worked. What about the other direction? Now, in the other direction, we're going to slightly refine our insertion rule. So we have this insert X with ID 4a after 1a. So 1a is the letter A here. So if we just insert the X directly after 1a, then we will be inconsistent with the left-hand side. So somehow we need to figure out that the X actually needs to go after the Q. And so the rule we're going to use here is as follows. We look at the ID of the new operation, which here is 4a, and we're going to say if the ID on the right-hand side is greater, then we're going to skip over it. So we first find the 1a, that's the place where we're inserting, and then we look at the ID of the character on the right-hand side, and we see this is 4b. 4b is greater than 4a. so we're going to skip over it. The next one we look at is 5b. 5b is also greater than 4a, so we're going to skip over it as well. Next one is 2a. 2a is less than 4a, so we're not going to skip over it. So that's the rule down here for skipping. So you look at the ID of the incoming operation and compare it to that on the right-hand side. And if we just check on the left-hand side that I didn't cheat earlier, this actually does work, because here we were saying insert the 4b after 1a. So after 1a, the next one is 4a, but the incoming one was 4b. 4b is greater than 4a, so we don't skip over 4a. So that still works. So we did no skipping on the left-hand side, but on the right-hand side here, this x skipped over p and q based on that greater than, less than rule. And then the x ended up in the right place. And then finally for the letter y, that then is fairly simple again. So this is insert the letter y with ID 5a after 4a. Well, the 4a has been placed here, so 5a comes after that. We don't do any skipping because 5a is greater than 2a. Does that kind of make sense so far? So it's not necessarily obvious that this actually does always converge. So we proved it. And that is in fact why I'm here in Vancouver, because we used some theorem proving software to prove that really in all cases, no matter what you do here, these rules do actually end up in a consistent outcome. And we wrote that as a paper and submitted it to a conference here called UPSLA, which is in town this week, which is what has brought me here. So we can prove that this thing really does always work, even if it's not necessarily obvious from just like glancing at it. But I find it quite a cool algorithm, because it's not too hard to understand, but it's still quite subtle.
It converges, but does it do what the user actually wants?
Yes, that is a good question. I have a picture coming up for that. So imagine your document says, "Hey guys," and we want to edit this. And on the one hand, we're going to somebody changes it to "Hey everyone," and somebody on the other side changes it to "Folks." Hey folks. And so remember what I said earlier about deletion. So deleting a character once, like we're deleting the G here. Well, deleting it once is the same as deleting it twice, so deleted is deleted. But the insertions, the insertion of everyone and the insertion of folks, both remain there. And so the outcome here will then be, "Hey everyone folks," or "Hey folks everyone," which is not really an English word, but that is just what we end up with based on applying this algorithm. So that is kind of the sad state of the art of these algorithms, really. Like, they will produce merged outcomes that are not necessarily valid English, but actually, if you imagine like trying to write the algorithm in such a way that it does always produce valid English, then it would probably be intractable. I think some people have actually tried that and just realized that it's intractable in practice. So we just stick with this simple heuristic of preserving both of the insertions. And this is in fact what things like Google Docs do. And a lot of people use it, and it seems to work well enough for people in practice. Of course, they have things like the hint of other people's cursor positions. So at least if you're both online at the same time, you'll get a hint that, oh, the other person is currently editing this paragraph. Maybe don't go in and edit that same paragraph at the same time. And people then kind of naturally adjust themselves to not trampling on each other's edits, hopefully. But just from a pure algorithmic point of view, really the best we can do here is ensure that everyone ends up in some kind of consistent state in which hopefully not too many changes have been thrown away. And then in the worst case, people might have to do a bit of editing afterwards to actually clean it up and turn it into something grammatically valid. But that's kind of where we're at. So the basic algorithms are there and they work. The challenge of stuff that I'm working on at the moment is how efficient can we actually make these things? So you saw we need a separate identifier for every single character in the document. That can add up to quite substantial overhead. Also, at the moment, we keep all of the deleted data. which is, again, adds overhead and also might add a privacy problem. If you want to send someone else a copy of the document, you don't necessarily want to send them the entire editing history up to that point, but you might want to just send them a snapshot of the current state. So that's another interesting problem we're working on. Want to have better support for moving subtrees around in a JSON document and doing that atomically and so on. So there's a whole bunch of interesting stuff that I'll be continuing to work on over the next few years, and hopefully we'll gradually figure this stuff out. But it's an interesting topic. If you want to play around with it, the open source implementation is there and kind of works, and I'd love to hear how any of you get on with it. There's another advert for my book. And I would love to take any questions from anyone. Please. What?
Might not be on. So.
Okay.
Hello. Okay. So in the example you showed earlier, could you talk about what would happen if the events were being delivered in this one? What would edit 5 be? What if it is received by A before edit 4B?
Yes, that's a good question. So this 5B needs to be received after this 4B, because otherwise the 5B doesn't know where to anchor its position. So the rule we use for that is we require a causally ordered delivery. So what that means is that there is an ordering on some of the messages, that some messages have to be received before others. And in particular, if the same user makes one edit and then makes another edit, then everyone must receive those two in that same order. Now, the network, the underlying network may actually reorder these things. So there's a piece in the code which then actually puts them back into the right order again. And so if you receive the 5B first, then it will actually notice, oh, I'm missing the message before, and it will buffer this message here and hold it for a while until the 4A comes in, and then it says, okay, now I can release both messages. So it just uses some internal buffering for that. You get a similar thing. So this is in the case where the edits come from the same user. You get a similar thing if you have 3 users and say user A inserts a letter, then user B deletes that letter. And so those are 2 separate operations, but the user B's edit depends on user A's edit. And so again, we then have that chained link of causality that requires that if there's a user C in the system, user C must receive the insertion from user A first, and then the deletion from user B. And so it keeps that ordering dependency as well. Do you want to go first?
Hi. So you chose the property of that as long as they are larger, you'll skip them.
Mhm.
Is that, out of curiosity, if you were to just flip the greater thans and less thans in that rule, would the property still hold?
No, it wouldn't work if you swap the rule around. So the reason for that requires a moment of thinking, but it's got to do with the causality that I just talked about. So I said that this 5B here comes causally after the 4B, because this 5B depends on the 4B. And also I said earlier, the rule for generating these numbers is that you pick always one greater than the greatest number you've seen. And so what this then implies is that if there's a causal dependency between 2 edits, then the edit that comes causally later, in this case the 5B, always has a greater ID than the one that comes causally before it. And so now here, in this case, what we want is that if you're going to start skipping, you have to skip over potentially a whole sequence of insertions that happened here until you get to the right place. So we certainly wouldn't want this X to end up between the P and the Q, because that really wouldn't make sense. So you would start interleaving things in a bad way. And so we depend on this causal ordering here. So if the 4b gets inserted first, the 5b depends on the 4b, but because it depends on it, it has a greater ID. So now if you're going to skip over 4b, because 4b greater than 4a, then we know that you must also skip over 5b, so and any letters that follow. So because the numbers only ever get bigger the longer that you go down the causal dependency chain, you can be sure that if you skip over the first one, you will also skip over all of the subsequent due to the transitivity of the ordering. I don't know if that made sense. It's a bit of a subtle explanation. But yes, so if you turn around, make it less than, then the whole thing would break. There's one at the back here. Should we have to you first?
So does it take into account who made the edit first, or do we just not care? Like, so for example, why is node 1 in green getting A's and, you know, numerical sort of A's, and then node 2 in purple is getting the B's, and why would they be greater than, or sorry, why would the A's be greater than the B's? Does that make sense?
Yeah, totally. So there's no timestamp ordering in here, if that's what you're saying. So it has nothing to do with the wall clock time at which these edits happened. That I will argue is a good thing, because people set their clocks to all sorts of random things. So better to just not rely on clocks at all. In terms of why they're called A and B, I'm just assuming that's arbitrary. Like, in a real system, maybe it would be like the hash of a public key or something like that. So it's just some pseudo-random identifier. Really, we just need to impose some kind of ordering on them. If you have a good way of defining what the order should be, then that's fine. You can use that as long as they're unique. But I think for many purposes, it's fine for it just to be arbitrary.
So if I understand this correctly, it's very close to the algorithm vector clocks, basically. That's what you're...
So vector clocks are what you use to get this causal order delivery. Yes.
Yeah, all right. Easy to remember then.
Yes. Oh, it's at least vector clocks are one way of implementing that. Yeah. Here at the back.
Doesn't this make node B like a master versus the node A being the slave or client node?
Not really. So with the typical like master slave, or I prefer to call it leader follower, with that pattern, you have all of the writes going through one designated node, the leader, which is not the case here. So the network that's used to transmit these things is completely arbitrary. It can be peer-to-peer, it can go via a leader server, it can do anything. You can have local Bluetooth if you like. So this is not making any assumptions about the network topology. Whereas the Google case of routing through the central server, there you can regard the central server as a leader effectively.
You mentioned reorders and moves are something you're still working on. Do you have an approach already in mind, even if it's not proven yet, perhaps?
Yes, I do actually. I thought of this only fairly recently, but actually the solution is remarkably simple. And so I'll talk for the moment about moving, say, one subtree of a JSON document to somewhere else. So what we do is we give each object, that is each map or each list object, we give a unique identifier. And in fact, we can just use these same number-letter combinations as the identifiers for those as well. They work perfectly fine. And now what we require is for the JSON document to be a tree. And so a tree means that each node has exactly one parent, except for the root node, which has no parent. But we don't want a node having more than one parent, because then it would be a DAG, not a tree. Or potentially you could even create cycles if you're not careful. So what we want is the constraint that each node has exactly one parent. Now, what happens if Sorry, no, let me show one picture. So here in this one, I had here a link operation, which puts an object as a sub-object of some existing one. And so what this does here is it refers to this ID1, which is the ID of the newly created map object. And the map is this by milk done false object. And it links it into the to-do list. And so what we can now do is, if there are several link operations concurrently that both try to link the same ID1 into different places into the JSON document, then we require that exactly one of them is the winner, because we need this ID1 to have a uniquely defined parent. And this operation is what gives the ID1 the parent. So now we can give an ID to this entire operation here and order by that. And the one with the greatest ID is the winner. And so that is the one that defines the parent of the ID1. And so now this gives us a way of implementing the move operation, which is that you simply have a link operation with some existing ID. And by the rule that each element must have exactly one parent, that will end up stealing the object from wherever it is currently in the tree and putting it in the place where you want it to be. And thus you get an atomic move. I don't know if that made sense. This is the first time I've tried to explain it in front of an audience like this.
If you have a node that sends an update and the other node doesn't have the information that the other one depends on to add to that, do you have like I don't have that node? Like, can they catch up? I don't know, it's hard to explain what I'm saying, but imagine like the purple node got something from a red node and added it, and the green node didn't have the red node one.
Oh, right. Yes. So the causal delivery should take care of that. So that will keep track of I received this message before I sent this other message.
But do I have to
and
will it send it along?
Whether you have to wait or not depends on the network protocol underlying this. So with the protocol that we built on top of WebRTC, it will forward on other nodes' messages. So you don't have to wait for the other node to be online. It will compare vector clocks, which is one way of saying it'll kind of does a diff between the two to figure out which messages you're missing, and then just send you in bulk all of the messages that you're missing to the other side.
You mentioned that you use some kind of proof assistant for formal verification. And the question is, did it really help you identify or encounter the bugs or some algorithmic inconsistencies?
So with the proof, we didn't find bugs in the actual algorithm. And the proof we did was on a fairly abstract specification of the algorithm. It wasn't on the literal JavaScript code, because it turns out that trying to prove something about like a 10-line snippet is hard enough. Trying to do it on hundreds or even thousands of lines of code is just way too hard. So proving stuff about code is still really, really hard, despite all of the tools that exist around this. So we didn't find any bugs in the algorithm or our particular implementation of it. We did find plenty of bugs in our thinking, though. And that's so as a learning experience, it was actually very valuable. So to give one example there, the definition of commutativity, that is being able to apply things in both orders and get the same result, turns out to be very subtle, because you can have operations that fail. And we need to account for the fact that operations may, in the case of this CRDT here, for example, a reason why an operation might fail is that it refers to some ID that doesn't exist. And in that case, we would then enter a failure state. And so the causal delivery is supposed to ensure that that never happens. So you never actually get to that failure state, assuming that the causal delivery is working correctly. But the definition of commutativity in this context is then very tricky, because you're not just saying two function must commute, but what the function does actually depends on the state to which the function is applied. And it took us like 4 or 5 attempts until we figured out the right way of just writing down this commutativity property, until we could then actually do the proof to show that you ended up in the same state. But yeah, that ended up taking a long time.
So are all nodes always going to require downloading the full history for every document there? And could you get around that without dropping the constraint that you'll never lose data?
So at the moment, the way it's implemented is, yes, everyone has to have the full history. We're kind of working on the hypothesis that if you represent the history in a compact way, then that's actually okay. Like, for example, if you clone a Git repository, you get the entire history of all of the commits, unless you do a shallow clone. And so, like, based on some kind of arrogant reasoning, like what is good enough for Git is good enough for us, we just said, okay, we'll see how far we can get with just keeping full history for now. So you could have a snapshot. You get into interesting problems of authentication there. Like, if you don't 100% trust the person who gave you the snapshot, can you still verify that the snapshot is consistent with the full history of operations that came before it? That is actually something that a PhD student I'm working on is trying to figure out at the moment. There's some very interesting cryptography problems there. But anyway, I got sidetracked. Whoever.
Hi, back here. Hello.
Oh, okay.
Sorry, am I jumping the queue here?
Go ahead.
I'm just wondering, is there any research that's been going on about adding access controls to this? Say, I want to take this paragraph and say this user can't edit it, but this user can, things like that?
I'm not aware of any research off the top of my head. I think, so if you do access control by policy, so if you just require all of the clients to be well behaved and obey the policy, then I think that would be reasonably straightforward. If you want to enforce the access control at a more fundamental level, like maybe a cryptographic level, then that would get substantially harder. There, I don't know, I'm afraid, sorry.
Hello? Yeah. If we are to use this to, say, merge code changes, can you guarantee that we will always end up with valid code?
No, unfortunately. Like in the same example as with the grammatically incorrect English sentence, I'm afraid there's... Actually, sorry, I backtrack a little bit. So in principle, you could represent the code not as a stream of bytes, but as a syntax tree. And if you do that, then you can apply all of these tree operations, and that actually should at least preserve the syntactic validity. You might still get stuff like passing too many arguments to a function or something like that, but that would at least make sure that all of your brackets appear in the right place. I don't know if anyone actually does that in practice, though, of like sending bits of syntax tree around rather than like the bytes that make up the source code file.
Do you have any way of detecting that you have a conflict, like in your folks everyone example? It seems that perhaps you could like reason out of the causality that, you know, there are two people editing the same thing, and therefore you might want to add some metadata to your document to say there's a conflict here that, you know, a human should look at or something like that.
Yeah, I think it would be really nice to like have some kind of pop-up saying that, hey, check this place. I think you would probably have to do it on the basis of some kind of heuristic in practice, because like you could still get a grammatically incorrect sentence by, say, whatever, say you have an adjective and a noun mismatched in terms of plurals. And so one person changes the adjective, the other person changes the noun. And so by having made both changes, then it's still grammatically incorrect. So what you probably need is some kind of like an edit was made within a distance of 4 words or something like that. kind of heuristic for alerting users.
Level detection, not really as part of the protocol. Could the protocol itself, like, if you have two edits to that, have a parent history that arrives at the same ID, or, say you deleted a whole stream of characters and then someone inserted and you got that later on, is there some way using your identifiers to maybe figure out that there was a conflict there?
Yes, so certainly, like, if, for example, if you have insertions literally in the same place, that would be quite easy to detect. But I was trying to say that even that is probably not enough, that you'll probably want a wider heuristic to catch more cases still.
Hi, just wondering, from your experience of implementing Automerge, how reliable is the assumption of eventual delivery? And when eventual delivery fails, let's say you miss a message, is that part of your proof that at least that once the message is failed, you don't diverge from the current state and you just keep within the same distance within the two diverged state?
So what we would try to do there is at the network protocol level to ensure that the missing things is retransmitted. So it doesn't just rely on, say, TCP or whatever the underlying network connection is, but in our case, with the implementation, it uses vector clocks, which is essentially a way of counting how many operations you've seen from whom. And you can tell from the counters if you're missing something. And so when two nodes communicate, they will then notice, oh, you seem to be missing this particular message here. Let me give that to you. And so it'll fill in the gaps then.
You also mentioned, because one of the answers that you mentioned that there's certain length of the buffer that you kept, or is that... Because like one of the message, for example, someone was asking that whether you receive 5B or 4B out of order, and you mentioned that for the buffer, there's a certain limit of that buffer, obviously, due to implementation. So let's say if in real life, do you experience issue that, oh, you got the limit to that buffer, and what happens if that buffer fail and you don't get all the messages?
So I think in the current implementation, it's an unbounded buffer, actually, because we're keeping the entire history anyway. We're kind of assuming these are small quantities of data that comfortably fit in memory. So it will just buffer things indefinitely until it's got the dependent messages.
Hi, yeah, so I was just wondering if you had a subtree, like let's say it's a list, and client A deletes the list, and then client B tries to insert into that subtree, like a link operation. What would you do in that situation?
So what the current implementation does, which I think is probably the most sane way of doing it, is to treat changes to each object as independent. And so if a link would be a change to the parent object that adds or removes a child object. And so if you make any concurrent changes to the child object, that's completely independent. So the changes are identified just by the unique ID of the object, regardless of where it is in the JSON tree. It's not that it uses the path from the root to that object, but it just uses this some kind of unique identifier for the object. And so that way, if you make a change to the child list concurrently, that will just happen. Even if that list is then actually removed from the document, it just means that the change is not visible, but it still happened.
Okay, so it would be like a link into a list that is no longer visible because it was already deleted? Yep. Okay.
And potentially there could be some kind of garbage collection then afterwards, which says, oh, like here, there's this object which is no longer part of the document. We're going to throw that away.
In your research, did you explore using any blockchain technology? And if so, what were your experiences?
Sorry, who am I looking at? Oh, there, sorry. Blockchain. No, haven't really been using blockchain. So in my view, blockchains are very heavy hammer that is applied to a bit too many problems. But
you're kind of doing the same thing.
Well, so a blockchain gives you a very strong guarantee, which is that this total ordering of the blocks and provides some kind of consensus mechanism around deciding what the next block is going to be. And so that is kind of even more extreme in some way than the central server. So the purpose of the central server is really just to enforce this total ordering. What a blockchain is in some way a distributed protocol of agreeing on some total ordering of those blocks. So if you have that, you can apply something like the Google Docs operational transformation algorithm because you have that necessary ordering, but you still have to wait. Every change you make would have to go and be incorporated into the next block before you can come back and then actually apply it locally. So it's possible to do things around there, but I prefer working in the context where you can have any network topology without forcing too much ordering onto the system.
Hi.
Hi.
What if you do a similar operation at the same time? Like a different operation at the same time?
Well, what do you mean with that? Like, do you mean inserting into a list or overwriting a key in a map, or what kind of operation are you talking about?
Say you like delete and add at the same time from a different node.
So if you delete, like we saw earlier with the example, the element still remains in the list, but hidden. So in here, for example, if somebody deletes the letter O, that 3A position will still remain in the list. It'll just be hidden from the application. And so that way the insertion will still know where to put the exclamation mark. One interesting case is what happens if somebody, say, deletes an entire paragraph of text and concurrently somebody changes a spelling of a word somewhere in the middle of that paragraph. So what our algorithm there will currently do is, whatever, say the spelling was to remove an E and add an S or something like that. The end result will be just a stray S that remains there after the paragraph around it has been deleted, which is arguably a bit strange. I've been trying to think about ways of fixing that by having range deletions instead of each individual character deletions. But range deletions get really hard if you have partially overlapping ranges. So if you have an answer for that, then I'd love to talk about it because I haven't figured it out yet.
I was curious how you update Automerge. Like, do all nodes also need the same version of Automerge running?
That's so far a problem we've punted on. This is part of the reason why you shouldn't use it in production yet. There will be some very interesting challenges around that. I think, well, you'll have updates at potentially several different layers of the stack. So there's potentially updates of Automerge itself, then updates of the application level data model that you've built on top of Automerge. And those schema changes would have to be handled in some very careful way, but that's a to-do item.
Hi. Could you connect this to some of the other work that's been done on CRDTs? Because what I'm used to in that literature is it's usually some sort of discrete math object like a counter or a set. And then you have to give up some of the assurances you're used to in that nice object when you make it a CRDT. Like it's a counter, but you can't subtract from it. And that gives you the commutativity and the other things. And this seems completely general. And are we giving anything up? Or where are the things, the assumptions that we're missing that would, in a strictly sequential system, would be retained, if any?
Well, there's certain invariants that simply cannot be provided. So like, whatever, if you wanted to, I guess a typical thing is guaranteeing that a bank account balance doesn't go negative. Or if you want to ensure that in a list of letters, each letter appears at most once. Or that you only sell one particular seat in a theater once and not multiple times. Those are all kinds of invariants that you cannot enforce in this sort of system. So enforcing those sort of things would require consensus then.
Have you formulated what the range of invariants that are not supported are in this particular data structure, or?
There is some theoretical work. It's in the database community on a property called iConfluence. There's some papers from Peter Bayliss and his research group on trying to identify exactly those database constraints which require coordination, i.e. some form of consensus, and those which don't. And they use that in order to improve the performance of database systems. So for example, they showed that enforcing a foreign key integrity constraint does not require coordination. But like the bank account balance, for example, requiring that something doesn't go negative does.
Thank you.
Another interesting thing is actually uniqueness. So often enforcing uniqueness of some arbitrary user-chosen value requires coordination. So for example, if you want to ensure that each username can only be claimed once, that there cannot be multiple users with the same username, that would require coordination. But if you have some kind of systematic way of generating identifiers like we did here, then you get uniqueness without coordination. So like if you require, for example, some kind of strictly incrementing sequence, then you do require coordination. But if you only require this thing where the pair of a number and a letter needs to be unique, then you don't. So you can play all sorts of tricks with that boundary there.
It looks like if you have, if you're tracking all existing clients, all existing nodes, you can implement some kind of checkpoints, where some operation of checkpoint where all nodes agree about current content and you can safely delete the history. Is it true?
Yes, that's true. The tricky thing is what to do if your friend has dropped their phone off a boat and it's now lying on the bottom of a lake, and that phone is never going to come back online again. And so I guess you can then apply some kind of timeout and say, okay, if you've not seen a device for more than 3 weeks, then just declare it dead and assume that no more changes are going to come from it or something like that. But you start having to like explicitly manage the membership in some way there. But yes, so there's a concept of causal stability that is sometimes used, which is a way of saying that everybody has seen all of the changes up to a certain point, and we know that no more changes are going to come in that are concurrent with these messages. Everything that is going to happen causally afterwards. That can be quite a useful property to use in some cases. Do I have any questions from women? I've only had men so far.
Or anyone in the back. We have another mic right here. You just have to walk up.
Is it my turn?
Yeah.
Well, I was just having a follow-up question. So if you want to implement that, you would need a central kind of coordinator though, right?
Yes, or at least some kind of agreement protocol amongst the remaining. So you could say that maybe a majority of nodes can decide to kick one node out or something like that. Is that what you're asking?
Yes, my head is still spinning around it, so I'm trying to imagine it in a decentralized way, but I'm not sure.
Sorry, imagine what's in a decent...
To make that decision that everybody has seen all the changes at some point.
Okay, yes. So there's a bunch of research on the topic of getting several nodes in a decentralized way to agree on something. That all falls under the headline of consensus. And it is also a pretty mind-bending area that I only barely understand. What is used there is to ensure that you can't have two different groups of nodes deciding contradictory things. You require a majority. So on the basis that if you have a majority of more than half the nodes agreeing to something, then there cannot be another majority that separately decides on some contradictory thing, because those two majorities would have to overlap. And so on that basis, you can then get a majority, but not all the nodes to decide on something, like, for example, to truncate the history at some point. But it would be a topic for another day, I suspect.
Oh, actually, sorry. Can you go back to the operational transform one for a second?
To which?
To the operational transform slide.
This?
Yes, this. So could you, instead of doing the transform and instead of having the server assign the total ordering, use on the commands, not the positions, the same ID assignment system you're using? So that would be command 1A, that would be command 1B, and then reorder the commands to be applied in order by ID.
Yes, there is an operational transform algorithm that uses that approach, I think. So what it would do is...
Because then you don't need the server anymore if you do that. Because the command, the ID ordering then is still globally unique.
Yes.
So you just have to effectively rewind if you get an earlier command to an earlier state and then play back forward again.
Yes, exactly. So that kind of undo, apply one operation, then redo the history to that point.
Which is
there is
what your move operation would be doing with your link command is effectively putting a versioning on the command, which would be doing that.
Yes. So there's a paper that describes an algorithm like that. I don't know if it's actually been implemented in practice.
Because if you did that, it would open you up to doing more than just things that reference a character position anymore. Now you can reference the results from a previous command. So now you can have a much more compound action being versioned effectively. Like your move operation,
yes,
compound action that's being versioned as opposed to a simple action, right?
Yes, you still have to reason about the trouble, though. What happens if some operation sneaks in ahead of you and changes the basis
you could
on
have
which
a
you're
future
operating.
command now has operations on an invalid state. That's like your overlapping range delete.
Yeah.
Okay.
I think there are solutions for it, but I'm not super deeply familiar with it.
Do you hand color enhanced syntax highlight all your slides?
Yes.
It's impressive.
I use an iPad and just draw them by hand.
Question: how would you handle an undo or a rollback operation? You know, if you have one of your nodes that created a change, and then at some point later on, potentially much later on, and chronologically he undoes this change.
Yes.
But taking that in, have a mechanism to take that into account.
So undo is actually a tricky topic.
Yeah.
Part of the reason it's tricky is that, say, if several people are making changes concurrently and you undo, whose change do you undo?
Correct.
So that's kind of a usability question, actually, about what people expect to happen. And I think the established answer now, at least from apps like Google Docs, is you only ever undo your own changes. You don't undo other people's changes. There's a separate function, which is totally somewhere separate in the user interface for reverting someone else's changes. But they take great care to keep those two concepts quite distinct from each other. So the kind of Control-Z or Control-Z undo is only ever undoes your own changes. And in order to do that, the best way of implementing that seems to be to keep a log of the changes you've made locally, and then to simply apply the inverse of those. So if the change you made was to insert something, then the inverse is to delete it again. It does mean you run into this problem of, say, I inserted a paragraph, then somebody else came and added a word to the middle of that paragraph. Now I undo the insertion of my entire paragraph. What does that mean? And I should actually find out what Google Docs does in that case.
All right.
I think it'll probably just remove the entire paragraph.
No pressure.
I did some experiments with Google Spreadsheets to see what undo would do. There's some like really curious cases where, say, I type 1 in a box, another user types 2 in a box. I type 3 in a box, other user types 4 in a box. I undo So my last change was to change the value from 2 to 3. So in that case, the value jumps from 4 back to 2, I think, even though the most recent change was actually changing it from 3 to 4. Is that the right answer? I don't know.
All right.
This might have recently changed, but last time I remember Google Docs with multiple edits, it just stopped being consistent as the number of users increased.
What do you mean stop being consistent?
It simply stopped making sense, and the edits stopped making sense. And you would write stuff and it wouldn't show up.
Wow. Okay.
Or you would delete stuff and it wouldn't delete, and the operations actually stopped operating correctly.
Was this fairly recently?
Last time I've been in a document with large enough number of collaborators was a few months ago. So yes.
Wow. Okay.
But that might just be server constraints on the single server.
I have no insight into what goes on internally at Google. I've had 1 or 2 conversations with people on the team. That's how I have this rough idea of how it works.
Found that throwing a large group of people doing a workshop into a Google Doc, collaborating, stating their goals for the day, is a very entertaining start to a day. Racing cursors.
I was wondering about, have you run into problems with group identifier conflicts? Two different clients or nodes join and they both select B, for example. Is there a similar thing where you must pick the largest number or that you've seen for your membership identifier, and then or is it you just pick a large enough number that it's going to not conflict?
Yeah, I think the best approach there is to pick something big like a UID or something that is extremely unlikely to conflict.
Okay. And then can you reuse your number, or is it confident that your you and you continue to use that every time, or is it something like every time you reconnect to something you should sort of pick a new identifier?
Yeah, so we did actually have some troubles with that because, say, if you write your files to disk saying, okay, my identifier is 1, 2, 3, 4, 5, and then at some later point you start the app up again and you read from disk saying, my identifier is 1, 2, 3, 4, 5. Well, what if someone launches 2 processes that both read from the same files? Now you've violated your guarantee. And many operating systems will quite happily let you run 2 processes like this from the same application. So on that basis, what Automerge actually does at the moment is to just generate a new identifier every time you start up the process, which means we churn through the identifiers really quickly. So as you shut down, restart, reload from disk, you're continually generating new identifiers. Now, the vector clocks I talked earlier have essentially a counter per one of these node identifiers, so they get bigger and bigger and bigger. So this actually becomes quite a problem because the network protocol becomes incredibly inefficient. So part of the work that I'm doing at the moment actually is trying to move away from vector clocks as the way of maintaining causality, and instead doing something much more like Git, where with Git you have each commit is referenced, is identified by a hash of its contents, and it references its parent commit, which is just one parent normally, or multiple parents if it's a merge. And you can trace through the entire history of commits by following those hashes. So you chain the hashes together in some way that is very vaguely reminiscent of blockchains, but it's partially ordered rather than totally ordered. And so we think that we'll probably actually be better off with that kind of hash chaining mechanism rather than vector clocks for maintaining the causal ordering, precisely because then you don't have this problem of having to choose an identifier anymore, because you're just relying on the hashes for the uniqueness.
So if you're using these UUIDs to identify users, isn't that like a relatively big number? So now every byte is now 20 bytes long?
Yes.
Okay.
Yes,
Just
the overhead is massive at the moment.
Yeah.
So I think for for text documents, we've probably got like a factor of 50 or so overhead there at the moment.
Ouch.
Yeah. I have ideas for reducing that. That's a project for the next couple of months.
Log in as a user on the document and then have a hash off of that or something.
Well, you can play tricks with the encoding. So you can, if you are using UIDs, you can rely on the fact that in a given document, there'll only be a fairly small number of distinct UIDs. So even though each individual one is fairly large, if you can compress them down in the appropriate, you might actually be able to represent it as just a couple of bits.
First time it's there.
Yeah, the first time
it's there, and then after that, use a hash or something.
So just use ideas from compression algorithms and columnar storage and such like.
One appeal of this structure is that it's not sensitive to latency variance, in the sense that if you have 3 peers and 2 are very quick to sync, and the third one is very slow, you'll still end up to converging to the same value. But it does seem that it might put... So first of all, is that a global property of all CRDTs?
Yes.
It's conflict-free, right? But does it mean that it will put an upper bound on the flexibility of the operations that are possible in the structure? And does that explain why all the CRDTs we have right now are fairly limited in scope?
Yes, so the CRDT has to be designed in such a way that you can apply the operations out of order and still get the same result. So that's this commutativity property that we were dealing with the proofs. And yes, actually designing them in such a way to make them commutative is not that straightforward. So that's why, like, if somebody designs a CRDT for a new data structure, that's like actually an academic publication. That's like some insight has gone into doing that. So I think we were the first to actually define a CRDT for this kind of JSON structure, although what we ended up doing in Automerge is not actually the same as what the paper describes, because we've found some really weird anomalies that happen there sometimes. So sometimes you can have things which have the convergence property, but just have really weird merge semantics. So part of the design there is actually in also designing the semantics in such a way that they're not too surprising for the people who use the data structures.
Well, that was one of the longest question periods we've ever had.
Wow.
Thank you.
Well, there's lots of really good questions. I really enjoyed this. Thank you very much all for coming. This has been great.